Assalamu alaikum. Miss Rubina is here. Today we start the third type of titration, that is redox titration. ठीक है, आज हम जिस टॉपिक को डिस्कस कर रहे हैं that is redox titration. Before this we have already discussed about the complexometric titration and precipitation titration and neutralization titration. Now today we discuss about the redox titration. As such, the name indicate that redox means that some redox reaction is taking place, and we also know that the redox reaction is taking place when we have the molecule has an ability to oxidized or reduced. So we categorize this redox titration and we perform this redox titration when our analyte is either an oxidizing agent or a reducing agent, or the analyte has an ability to oxidize or reduced. So we can find out the unknown concentration of our analyte that is either an oxidizing agent or a reducing agent with the help of this redox titration. So before this, we first must know that what is this oxidation or reduction. Oxidation, we can define this oxidation and reduction in terms of hydrogen, in terms of oxygen, or in terms of electrons. So we can define on the basis of either the substance that has an ability to oxidize or reduce. We can define the reduction, that is a substance that's undergo there is an addition of hydrogen or the removal of oxygen or that gains the electron, or depends upon the oxidation state, either the oxidation state is increase or decreases. We have the different definitions. ठीक है, and on the basis of this definition we have different oxidizing or reducing agent. हमारे पास कुछ oxidizing और reducing agent है. The common oxidizing or reducing agent, these are the different definitions of oxidation and reduction. And we just concern about here about the oxidizing or reducing agent. A substance that is able to oxidize the other one is self-reduce. That is the properties of oxidizing agent, or the reverse one, that is the reducing agent, has the property that reduces the other component but self-oxidized. Okay. And these are the basic properties of oxidizing and reducing agent. An example of oxidizing and reducing agents are, for example, the oxidizing agent, we have potassium permanganate, we have ferric sulfate, we have potassium dichromate, we have iodine, we have potassium iodate, potassium bromate, seric acid. We have a lot of different oxidizing agents are present, and also the oxygen, that is also a mild oxidizing agent. And mostly these oxidizing agent that is used in redox titration as an titrant, that is a substance of known concentration. And on the basis of the titrant we use, we have different type of redox titration. If we use the potassium permanganate KMnO4 as a redox in titrant, then as a titrant, then the type of the titration, that is called the permanganometry. Similarly, if we use the ferric sulfate, the type of the titration is called the serimetry. Potassium dichromate, then the titration is called the dichrometry. And if we use the iodine, then we have ID and iodometry. Okay, these are the most common type of titration. Otherwise, including that's iodine, we have iodometry, and if we have the potassium bromate, then we have bromometry. Similarly, if we use the other type of the oxidizing agent, then we have different type of redox titration. Okay, depending upon the type of the oxidizing agent we use. These are the common example of oxidizing agent. KMnO4, that is the secondary standard one. Potassium dichromate, that is also, this is a primary standard one. Okay, seric sulfate, because there is some solubility issue, so it is also considered under the heading of secondary standard. Otherwise, after the standardization or after it's overcome its solubility problem, it is one of the best oxidizing agent, that is a very stable one. Okay. Potassium dichromate, that is a primary standard one, is a stable one. It's a very good oxidizing agent. Okay. Then after that, you have then iodine. Iodine has, it is also a secondary standard one because of its volatile in nature. It is photolipid is also one. And so it is also a secondary standard, needs to standardize it. And potassium iodate here, or that is iodine, that is also a secondary standard one. The only one that is a very good primary standard, we have potassium dichromate. Okay. Then after that, the different example of reducing agent. The reducing agent, we have ammonium iron sulfate, and mostly, and also we have the iron ethylene diamine sulfate, sodium thiosulfate, and arsenic trioxide, and sodium oxalate. And also the potassium iodide, that is also a very important reducing agent. Tartaric acid, citric acid, that is also a very important reducing agent. And among these, this potassium iodide and sodium oxalate, arsenic trioxide, these are the primary standard one. And sodium sulfate, that is secondary standard, need to standardize in. Most of the molecules that contains the water of hydration, they are considered as secondary standard one, except that of arsenic trioxide and sodium oxalate, that also contains the two water molecule, but both these two, one is the primary standard along with that of a potassium iodide, along with that of potassium iodide. So vitamin C, that is also a very important reducing agent, and that is also important pharmaceuticals that is needs to be quantified or by estimated with the help of these redox titration. So one thing that is very important in during the titration, that is your analyte or your titrant. So among these, one is act as a titrant and other is your analyte, and some other pharmaceuticals that also contains a reducing agent or oxidizing agent, that is also used here for the quantification. The third important thing that is very important here, that is indicators. Common indicators. I also give you the handout, and I think you have your handout, and also consider it here. So I have the handout. Okay. The first page that contains the different definitions of redox titration, and then after that, it contains the different type of indicators that is used in the second page. You have the different type of the indicators that is used in redox titration. So important thing is the type of redox indicator. Redox, we have three different types of redox indicator. We have that is self indicator, we have internal indicator, we have external indicator. Okay. Number one, that is the self indicator. Basically, these are the different titrants. These are the different titrants, and have the different colors in oxidized or reduced condition. So whenever they have the different color in oxidized or reduced condition, then they used as a self indicator. Like when we have a KMNO4 is a purplish color in oxidized state, and the reduced state, it is colorless. Okay. इसी तरह iodine, when it is a oxidized state, it is the brownish yellow and the colorless in a reduced state. Cerium is a bright yellow coloration at the oxidized state. When completely reduced, it is the colorless one. So in these cases, when there is some color change during the reaction and the color change of the titrants, no indicator is added. It also indicates that this titrant indicates the end point, and this type of indicator that is called the self indicator. Okay, and the second type of the indicator we have, that is called the internal indicator. As such, the name indicate that it must be added in the titration one, that is added in the reaction flask, that is and have some oxidized and reduced color. They have some different color in the oxidized and the reduced one, or depending upon the concentration. ठीक है, 1:10 की concentration होगी जब oxidized and reduced, then it shows the some different color change. Okay, and this internal indicator basically are the indicators that has an ability to oxidize and reduce and have distinguished color in its both form. Its oxidized and reduced form have the different color. And the most common indicator that we used as an internal indicator, we have ferroin, we have sodium and barium salt of diphenyl amine sulfonic acid. That is most commonly used indicator, internal indicator. And ferroin and diphenylamine, that is the most commonly used internal indicator. They have different color in oxidized or reduced form. These are the internal indicator, and the choice of the internal indicator is very important. Which internal indicator we use, we choice of the indicator we discussed later. ठीक है, इसे हम थोड़ा सा अभी थोड़ी देर बाद डिस्कस करेंगे कि हम इसे किस तरह से चॉइस करते हैं. फर्स्ट वी डिस्कस्ड ऑल अबाउट द इंडिकेटर. Okay, now starch is also used as an internal indicator. Starch को भी हम जो है वो internal indicator के तौर पे use करते हैं. But starch is not a redox indicator, because we discussed that the definition of the redox indicator have different color in oxidized or reduced form. So starch will not oxidize and reduce, but it is a very good, have good combination with that of iodine, and shows a color change, a significant color change when it's combined with that of an iodine. So it is used in redox titration. But whenever you have a question, is starch is a redox indicator, your answer is that no, starch is not a redox indicator, but we use whenever we have a titrant, that is iodine. It gives a very sharp color change, so you can, so we have a very good result or estimation with the help of this starch. ठीक है, स्टार्च जो है वो आयोडीन के साथ अच्छा कलर देता है, इसकी वजह से हम इसे यूज करते हैं. अदरवाइज दिस स्टार्च इज नॉट रिडॉक्स इंडिकेटर. ठीक है, देन आफ्टर दैट यू हैव एन एक्सटर्नल इंडिकेटर. व्हेन वी यूज एक्सटर्नल इंडिकेटर, व्हेन योर एनालाइट मे रिएक्ट विथ योर इंडिकेटर. अगर एनालाइट रिएक्शन कर ले इंडिकेटर के साथ और some irreversible reaction is there, so we place this indicator outside the reaction flask. So we place this in a small grooves plate that contains the small amount of indicator, and mostly it is the starch iodide paste that is placed in small wells. And after adding a small amount of a titrant, after mixing the reaction mixture, we take a very small amount of the reaction mixture in the form of a small drop. And when we place this on the external indicator, if some color change is appear, it means that the reaction is completed. ठीक है, हम one by one after adding the titrant हम add करने के बाद reaction को जो है वो check करेंगे कि either the reaction is complete हुआ है, is completed or not by reacting with that of indicator that is present outside the reaction flask. ठीक है, कुछ condition ऐसे जिसके example हम आगे discuss करेंगे. Now we have our analyte, we have our titrant, and the third thing that is our indicator. When we perform this one, a direct titration, when it fulfill the conditions required for the direct titration. Otherwise, we perform the indirect titration or the back titration. Okay, we can perform both type of the titration depending upon the reaction is fast or the complete or the stoichiometry of the reaction. We have different type of the reaction. So we discussed earlier that we have different type of titration depending upon the titrant we use, depending upon the titrant we use. So the first type we have, that is when we use the per magnetometry. Okay. The first type of that is the potassium permanganate, when we use the potassium permanganate. As such, here there is some color change in an oxidized or reduced form. This is the some properties of potassium permanganate, its solubility and its color. Okay, these are the properties of potassium permanganate. It is a strong oxidizing agent, a strong oxidizing agent that is also used as a self-indicator. As we discussed earlier, it's have a different color in oxidized or reduced state. Oxidizing agent here that has an ability to oxidize the other one and self reduce. It is one of the strongest oxidizing agent. Why we call it is a strongest oxidizing agent, and another is a is a is a weak oxidizing agent. All of these oxidizing nature of a molecule that depends upon the redox potential of a molecule. And I think or suppose that you know very well about the E naught or the redox potential of any elements that is calculated with the help of standard hydrogen electrode by supposing it's that is present have a zero reduction potential. Then on the basis of that we have some negative and some positive values of redox potential. What is this redox potential? That is the power of reduction. Power of reduction, jitni zyada power of reduction hogi, they has an ability to reduce more. So this when we compare the different oxidation potential of the molecule, then we know that this KMNO4 that have different redox potential at different media, in acidic media and alkaline have different redox potential, its ability of reduction. Now this magnesium that has a redox potential of 1.5. It's the redox potential जो है at acidic media, that is 1.5, and the redox potential of potassium chromate is 1.33. So which one is a more strong one? That is KMNO4 that has a value of 1.3. And both of these molecules, as we discussed, that is the KMNO4 and potassium dichromate, that is an strong oxidizing agent. But when the reaction is between KMNO4 or potassium dichromate, then which one will oxidize and which one will reduce, which one act as an oxidizing agent and which one act as a reducing agent, that is depend upon the values of E naught, that is the reduction potential. So whenever the reaction is there, because the redox potential of KMNO4 that is more as compared to that of potassium dichromate, so potassium permanganate, it acts as a strong oxidizing agent. In the presence of this, the KMNO4, that's potassium potassium dichromate, it will oxidizes in the presence of potassium permanganate. Potassium permanganate act as an oxidizing agent, and potassium dichromate, in the presence of this, it act as a reducing agent. It will oxidize it or self reduce. It will oxidize, reducing agent that is reduces the other or self oxidized. Okay. So depending upon the value of redox potential, we can know that we know that which one will oxidize or reduced one. Okay. So we can't say that it is an oxidizing agent, a very perfectly one, no, because in the presence of a very strong oxidizing agent, the other oxidizing agent, that it will act as a reducing agent, like potassium chromate that act as a reducing agent in the presence of potassium dichromate, because it has a very good power of oxidizing agent. So ऑक्सीडाइजिंग एजेंट है हमारे पास, दैट इज इट इज एन ऑक्सीडाइजिंग एजेंट एंड पोटेशियम परमैंगनेट हैज द, ठीक है, हैव डिफरेंट ऑक्सीडेशन स्टेट्स है इसकी, and oxidation state depending upon in which pH it is present. It is, if it is a acidic pH, it's reduces, completely reduced to manganese ion, and if it is incomplete in the neutral or the alkaline medium, then reduces the brown solid manganese dioxide, or in strongly alkaline solution it is converted into the green magnate ion. But depending upon the number of the electron reduction, that is the gain of electron, number of electron, its gain. ठीक है, here the reduction taking place by taking the um, from +7 to +2, the number of electron involved, that is the 5 1. ठीक है, दिस अ वेरी क्लियर पिक्चर, ये बहुत ही एक क्लियर पिक्चर है यहाँ पर कि आपके पास KMnO4 इज अ पावरफुल ऑक्सीडेंट, that the most widely used, ठीक है, and strong pH के ऊपर in the presence of sulfuric acid, and you also observe that in all of the condition some media is also there, that is sulfuric acid, some HCl or strong or the acidic or the alkaline media is there, because whenever the electron transfer reaction is taking place, the some mediator is there, so acid that is used and involved in the electron transfer reaction. ठीक है, in the acidic medium it involves the 5 electrons with its redox potential is 1.51, and in the neutral and the acidic, feebly acidic or the neutral medium involves the 3 electron with the electrode potential of this one, redox potential, and in the alkaline media only the 1 electron and its gain and redox potential is very low, that is 0.558. Is this manganese that is whenever we use as a titrant, is a secondary standard or primary standard? We discussed earlier, it is a secondary standard, needs to standardize it, needs to know the what its concentration, what make its secondary standard. One, 2 or 3 important points that makes is the secondary standard. One, that is potassium permanganate is not primary standard because traces of manganese oxide are invariably present. इसके अंदर जो है ना manganese dioxide as an impurity is present. When some impurity is present, then it is called the impure one or the secondary one. So it must be need to be standardized one, and we standardize it with the help of a primary standard reducing agent, that is sodium oxalate. Sodium oxalate की थे, that is a reaction between the KMnO4 and the sodium oxalate, how it's react one, ठीक है, how it's react, number of the electron involved, that is very important to calculate the gram equivalent weight of the molecule, that is equals to 10 equivalent. ठीक है, हमारे पास that is we use, and how to prepare the solution. One thing again, where even if we use the distilled water and that contain the some organic impurities, that will also causes the instability of this KMnO4. So any impurities or the grease or any impurity that converts this potassium permanganate into manganese dioxide, and manganese dioxide that is promotes to auto decomposition of permanganate. So that is a secondary standard one, and needs to be standardize it with sodium oxalate. That is a simple definition we already discussed earlier about the oxidation and the reduction one. We only considered here potassium permanganate. It's a redox titration, and this depending upon the titration is performed, it is used, it is can be it have a different oxidation state and can be used to find out the quantitative analysis of ferrous ion, or that is also used to find out the nitrate or peroxidate or oxalate ions. ठीक है. Hydrogen peroxide is analyzed with the help of permagnetometry. ठीक है, have different oxidation redox potential value, and why this ferrous or say the chloride tin that is that can be quantified by with the help of this potassium potassium permanganate, because depending upon its standard redox potential, this act as an oxidizing agent and have a low one. Then ferrous that is 0.7. No indicator needs to be used, because a self indicator, it's a very good self indicator, indicates the end point very clearly. ठीक है, और different conditions के अंदर we already discussed that about this potassium permanganate. Now this is all about that of potassium permanganate. Now the second type of the titration we have, that is iodometry and आइडीमेट्री. सेकेंड टाइप है आपकी टाइट्रेशन की, वो है iodometry. And no, we discuss about first about the dichromatometry. ठीक है, dichromatometry as such we have, that is we have the second type of titration in which we use the titrant, that is potassium chromate, that is called a dichromatometry. ठीक है, dichromatometry in which the titrant is potassium dichromate. Potassium dichromate, as we have discussed earlier, that potassium dichromate जो है वो आपका potassium dichromate, that is a primary standard one. ठीक है, potassium dichromate is a primary standard one, and this potassium chromate that is a very stable one. It's a pure one, and most commonly it is used for the quantification due to its primary standard nature. ठीक है, and it is present in the oxidized form. It's a very orange crystals is present there, orangish crystal is there in oxidized form. ठीक है, oxidized form में इसका जो color होता है वो orange होता है potassium dichromate का, and then it is का reduced form, it have a different color, depends upon the its oxidation state. Oxidation states के ऊपर that it have the different color. ठीक, potassium dichromate mostly it is used to quantify the iron one. Iron को ये ज़्यादा quantify करते हैं with the help of this potassium dichromate. ठीक, और in the acidic media it's chromate with the acceptance of 6 electron is converts into the chromate 3 ions and reduces from this chromate 6 to that of chromate 3,1 in the acidic media. And internal redox indicator, mostly which indicator we use the diphenylamine and phenylenthranilic acid, diphenylsulfonic acid, that is most commonly used indicator in this case of titration. We have different type of indicator is there. We have different type of indicator, and indicator mostly here we use the barium and the sodium salt of diphenylamine. Diphenylamine is most commonly used. Okay, choice of indicator is very important here. Choice of indicator is very important here. How we choose this indicator, I have an image there. Okay, how we choose this indicator here. We have different type of the indicator. We have diphenylamine, diphenyl benzidine, barium or sodium salt of diphenyl sulfonate, and phenylenthranilic acid and ferroin, and have different redox potential value. Inki different redox potential value and have a different color. In reduced form, mostly in the reduced form, it is colorless. Most of them are colorless. And in oxidized form have a different color. That's a quite sharp color change from a colorless to blue, from a colorless to blue walrus, from a colorless to red, from a colorless to purple one, deep red to pale blue, have a different color, so it can endpoint can easily be detected. But one thing, that choice of this indicator, which indicator is used. For example, if we have an oxidant is chromate and reductant they have iron 1. So the choice of indicator, which indicator we can choose it here, depending upon the two things, is that the redox potential of the indicator that must be higher than that of the reductant, that must be higher than that of the reductant. आपका जो reductant की redox potential है इससे आपकी ज़्यादा होनी चाहिए, and that must be lower than that of oxidant. For example, here we choose the indicator that is barium diphenyl sulfonate. Diphenylamine sulfonate have a redox potential value of 0.783. 0.83. We can't choose 0.76 because this is lower than that of 0.77. That is your reductant. So one thing that is very important, how we choose this, the redox potential of this one is more as compared to that of your this one. So it can easily be oxidized as compared to that of this one because it has a high redox potential value. When we perform the process of titration, there is a reaction between the titrant. The first reaction is between your titrant and your analyte. When all of your titrant is consumed, then the second reaction starts from the titrant with that of an indicator. So redox potential is very important here because we know that if we have a more redox potential, then it has a property of more reducing one that can easily reduce and that can easily reduce one. So here the oxidization taking place with the help of oxidation, that is an oxidizing agent, it will first oxidizes the titrant that is 0.77 that can easily be oxidized and self reduced and self easily reduced because have a low reduction potential value. When all of these molecules that can be consumed after this, then this redox this reductant or this oxidizing agent oxidant, then it react with that of indicator and then it will oxidizes that. First oxidizes all of the analyte and then after that oxidizes this indicator, so it shows the color change. Initially it is the colorless. Initially, it is the colorless, it is present in its reduced state, and when it is oxidized with the help of an oxidizing agent, then it shows the color change, that is red violet coloration is there. So this important point is very important. Go through it several times here, what it is mentioned there and why it is necessary. Okay, that is also important point relating to that of indicator relating to. So this is the second type of indicator. Now we discuss about the third type of titration, that is about the IDO and ID-metric titration. IDO and ID-metric type of titration in which we discussed about the titrant, that is iodine. Iodine that can be used by two type, that is the direct and indirect titration. Okay, if a direct titration with iodine, then it is called the ID-metry. If an indirect with iodine as a titrant, then it is called the idometry. And both of these reactions that is performed in the weak acidic or the weak neutral media, whenever we have a high acidic media and high basic media, then iodine will not present in its original form. It's convert, it react with that of oxygen. Okay. Now the first we discuss about the idometry, that is an indirect method. Indirect method in which iodine is liberated during the reaction, and the liberated iodine that is utilized for the quantification of our analyte. So how we perform that is that the quantitative analysis of the solution of an oxidizing agent by adding an iodide which react to form the iodine. The iodine is produced during the reaction media. Iodine will liberate it with the help of iodide. So with the help of some oxidizing agent that react with that of an iodide and convert this iodine, and the release iodine that is treated with another species for the quantification, and mostly it is used for the quantification of standard sodium thiosulfate. Sodium thiosulfate, that is a secondary standard one. It can be standardized with the help of this liberated iodine, and we know that there is a very good reaction between iodine and thiosulfate. ठीक है, बहुत अच्छा reaction होता है. This is the practical determination that the first step is done by the reaction between the oxidizing agent, potassium chromate, that is an oxidizing agent, and then potassium iodide, that is a primary standard one. Both of these two are the primary standard ones. So the liberated iodine, that is a very quantitative one. Okay. Potassium iodide react with that of an oxidizing agent and converts into the iodine. This iodine will liberated, and this liberated iodine react with sodium thiosulfate to give into the sodium thionate, gives the sodium thionate. ठीक है, इससे बहुत अच्छा react करता है with that of a sodium thionate, and that we can easily be quantify. That is called this is the back titration one, because the iodine and the excess of iodine is there, excess of potassium iodide is there, then iodine will produces, and this iodine that is treated with that of sodium thiosulfate for its quantification. ठीक है. And then after that, that is the simple iodimetry in which the iodine is directly used. But one thing that is very important here, iodine is not easily solubilized in water. So with the help of potassium iodide, we convert into the triiodide, and this triiodide, it behaves like that iodine, and the structure iodine that is used as starch is used as an indicator, because we know that starch is a very good combination with that of an iodine. Iodine, with the help of reducing agent, it is converts into the 2-iodide. We know that this iodide, that is iodide or iodine, 2 electron is involved for its oxidation or reduction, for its oxidation and reduction. Cannot be performed. But one thing I also want to share with you, that is about the solution of this iodine. No. Yes. So must take a snapshot of this page. The use of iodine as a titrant suffer from 2 major disadvantages. Why this is considered as secondary standard, because first, iodine is not particularly soluble in water, and second one, that is iodine is somewhat volatile. And we also observe that in the lab or in the storage, that iodine is mostly stored in the ambered glass bottle, because this iodine, that is also the photolabile one. Okay, so there is an escape of significant amount of dissolved iodine from the solution. So both of these disadvantages are overcome by adding the iodide to the iodine solution, because this iodine, that is covalently bond, and it is a very stable one, not easily solubilized, so converts into the ionic form. It's react with that of an iodide, and in the presence of this iodide, iodine react to form the triiodide, and is an ionic one that can be easily solubilized, and it is not the volatile one. So whenever I ask you in the exam why the iodine or the this is called a secondary standard, and how to overcome the problems with that of iodine, so you have the answer, that's by reacting with that of iodides, convert into the ionic form. So it can be easily solubilized, and it is converts into the non-volatile 1I2 plus I dash. I negative converts into the triiodide, and that behaves like that of iodine. Whenever it reacts, it needs a 2 electron. The simple, that for its oxidation and reduction, that needs a 2 electron. And we also discussed that it is a very good reaction with that of a sodium thiosulfate, and converts into the tetrathionate. Okay, converts it into the tetrathionate. Okay, you must cover this how we overcome the problem that is related to that of आयोडीन. ठीक है, आयोडीन के साथ जो प्रॉब्लम है वो हमें डिस्कस करनी है. ठीक है, then not perform into the very strong basic condition, or not perform into the very high acidic condition, because the iodine to form the various oxy halogens or react with that of a hydrogen के साथ भी react करके convert हो जाएगी in the acidic media. The iodine tends to get the oxidized, ठीक है, tends to get the oxidized हो जाता है. So we are going to perform this in a weakly acidic or the weakly basic media. So we have discussed about the permagnetometry, chromatometry, and iodometry. If we discussed about the cerium sulfate, that is a very good oxidizing agent, but it increases the it's enough one regarding the redox titration. Go through all of these things about the titrant, and different type of the reaction that is taking place here with KMNO4, with potassium dichromate, with iodine. ठीक है ना, how we choose the different type of the indicators during the reaction. One thing I also want in continuity to discuss in continuity with that of an iodometry and iodometry, that is a type of the reaction that is called so it is no we discuss it here, the type of the reaction that is also taking place with that of iodine. Okay, we have discussed here, that is diazotization titration. What is this diazotitration? Diazotitration, it's a reaction, or we can use this type of the titration to quantify the different type of the substance like benzocaine, procaine, or all of the sulfonamides that contains the primary aromatic amines can be quantified with the help of this diazotization reaction. We consider this diazotization reaction in the redox titration. Why we considered it here as a redox titration, where the redox titration is taking place here. So we discussed here about this diazotization reaction. This diazotization is positive with that of sulfonamides groups, primary aromatic amine, when reacted with that of a titrant, that is sodium nitrite, NaNa2, with in the presence of a maximum amount of an HCl. 3 HCl is there with a 1 mole, 3 moles of HCl is there. It is converts into diazonium 1. That is diazonium. What is the 2 nitrogen that is attached with that of a double or the triple bond? Then it is called the diazonium salt. And you know that this diazonium is formed with the help of this nitrous acid. How this nitrous acid is produced with the help of HCl, we have discussed it here. This is all about the diazonium 1. This is all about the diazonium 1. How this diazonium is formed? That is a reaction, diazonium compound or the diazonium salt, or the group of organic compounds sharing a common functional group with the characteristic structure of Rn2. Either it is double bond or the triple bond that is present with the help of it. We don't need this, we just wants to know that where this redox reaction is taking place. The reaction is quantitative under the control condition of the temperature approximately 15 degrees centigrade. We need a low temperature nearly to that of a -5. This is the mechanism of the redox reaction, how the redox reaction is, but we don't concern here. We just simplify it or reduce the content of the this redox titration. We just go through the where the redox reaction is taking place. The simple reaction is the NaNa2 react with that of HCl, converts into the nitrous acid, and this nitrous acid converts this one into diazonium salt. This is our required structure. And the second one, here, the redox titration is taking place. It is a type of external redox indicator, and the redox indicator, instead of redox indicator, we use the starch one, because we know that whenever the iodine is there, a starch that shows a very good reaction. Starch shows a blue coloration that shows the end point with that of iodine. How this reaction is taking place? Because we know that if we add the starch, in the reaction class, it will react with the analyte, sulfonamide, or it will react with that of a nitrous acid. Just so we can't add this starch in the reaction media. So how we find out the endpoint? With the help of an external indicator, we have a starch iodide paste or the starch iodide paper we have that is present outside the reaction class. So when the reaction is completed, when all of the sulfonamides that is reacted with that of nitrous acid, and with all of the nitrous acid, the first it's converted into the nitrous acid, that is a strong oxidizing agent. That is a strong oxidizing agent. Okay, but the reaction is not oxidation in reduction one. Okay, in the presence of this, so NaNA2, that is a primary aromatic amines, nitrous acid, it converts into the diazonium, and all of the primary aromatic amines is consumed. Then excess of nitrous acid is present there. Excess of nitrous acid along with that of an HCl is present there. And when we this potassium iodide, that is your indicator, in the presence of an HCl, it is first converted into the hydrogen iodide, and this hydrogen iodide in the presence of nitrous acid kahan se hamare paas aayega? That's Na2 react with HCl converts into the nitrous acid. So the reaction between this hydrogen iodide and nitrous acid, it is an oxidizing agent, it is a reducing agent. Also the redox reaction is taking place here. Kahan ho raha tha redox reaction? That is taking place here with the indicator. ठीक है, तो Na and nitrous acid react, that is an oxidizing agent, react with this reducing agent, that is the hydrogen iodide, and then this oxidizes this iodide and converts into the iodine. Whenever the iodine is there, then iodine combined with that of an starch and converts into the blue coloration. Okay, that is the example of external indicator to find out the endpoint with that of iodine. With that of an iodine, your indicator initially it is present starch with iodide, so no color is there. We know that starch when react with that of an iodine, then it shows the blue coloration. जब ये iodine के साथ react करेगा तब blue, not with that of iodide. Initially, it is present in the form of iodide. When we add an excess amount of nitrous acid along with that of an HCl, HCl first convert into the hydrogen iodide, and nitrous acid, the reaction between that and iodine will release, and released iodine make a complex with that of a starch that shows the end point. This is all about the diazonia point. Okay, this is all about the diazonium. ये आपका diazonium था. And I also want to share that this is also used to find out this iodine. That is also used to find out the penicillin, the how much amount of the penicillin that is present in the active form. We know that this penicillin that contains a beta-lactam ring, a 4-member ring that contains a beta-lactam ring, and beta-lactam ring that is a very unstable one that can easily be hydrolyzed. So if it is hydrolyzed, that it will open it, and it is inactive one. So if we wants to know that how much amount of the beta open ring form or the inactive form of the ampicillin is there, then how we find out? With the help of this iodine. Iodine can only be react with that of this open form of beta lactam ring. When the lactam ring is open, it will react with iodine. 1 mole of the ring open form of the penicillin will react with 8 equivalents of iodine. This is the stoichiometry of the reaction, by which we can calculate how much amount of the ring open form is present. That is 1 mole of the ring open form of penicillin will react with 8 equivalents of iodine, equivalent weight of iodine. The interlactam ring will not react. In this type of the titration, excess of the iodine solution is added to the sample of the penicillin, and the iodine which is not consumed in the reaction is estimated by the titration with sodium thiosulfate. As we know that it is very good to have a very good reaction with that of an iodine. So quantify the leftover volume of the iodine. Quantify the leftover volume of iodine. So this is all about this, or this iodine that can, in the case of iodimetry, when it is present in the burette in the form of triiodide, it will easily react with that of that can also be quantify the ascorbic acid, that is vitamin C. So that can easily be quantified the vitamin C. So it is your assignment, or you can write the equation between the iodine and vitamin C, because vitamin C, that is a reducing agent. Iodine, when react with that of a vitamin C, it converts into, that is converts into the dihydro, है ना, तो हाइड्रोजन उसमें से निकल जाएंगे, dihydro ascorbic acid convert into the dihydroascorbic acid with the liberation of 2 hydrogen iodide. So find out the reaction between the iodine and ascorbic acid, and either which one is oxidizing or the reducing agent, kaun sa isme is there's a hydrogen is involved or the oxygen involved during this reaction. Prepare this reaction for the exam. This is all about the redox titration. Go through the lecture you have. That also contains some application, that is industrial application, pharmaceutical application, and the last one, that the application you have, that is nutritional application, to find out the different components. So go through this one along with that of this lecture. This is enough for your final exam. Okay, prepare it. If you have any problem, you will ask in your physical class, or you will ask in my room or in my office. Okay, thank you. Allah Hafiz.